Hello there, and welcome to Fall Asleep to Astronomy. I'm so glad we found this quiet together. Allow the stillness of this moment to settle around you, like the soft, velvet darkness of a clear night. Let the world outside fade, and your thoughts become gentle, wandering sparks in the vast, calm space of your mind. Tonight, we're going to look at one of the universe's most tender secrets, the perfect, simple geometry that connects planets, stars, and even droplets of dew. Have you ever noticed how everything immense in the cosmos seems to adopt the same gentle curve, the same comforting symmetry? We'll whisper about the subtle, hidden force that shapes worlds and holds the galaxies together, a power so ancient and profound that its favorite form is simply a perfect sphere. We'll follow the quiet trail of this universal principle, moving slowly until the secret shape of gravity feels a little less mysterious. If these gentle explorations help you find peace or spark a quiet curiosity, consider offering a soft like and a gentle subscribe. It truly helps others find their way to this restful space, one unhurried soul at a time. For now, relax completely. The universe is patient, and we can begin our peaceful discovery whenever you are ready. Out in the quiet spaces between stars, there's a kind of soft, invisible tug-of-war always unfolding. Every world you've ever seen in a picture, every globe in a classroom, every curved horizon you've watched swallow the sun is the result of that quiet struggle. On one side is gravity, the universe's patient hand, always pulling inward, always trying to gather everything toward a single center. On the other is spin, the restless motion that refuses to sit still, stretching things outward, tugging at their edges, spreading matter and energy in circles. When a world is just beginning, there is no solid surface yet, no mountains, no oceans, no familiar ground, only a cloud, a loose, drifting mix of gas, dust, and ice, slowly collapsing inside the messy cradle of a young star system. That cloud turns, even before it knows it's becoming a world. It turns because the nebula that birthed it once turned too, and the universe keeps such motions carefully. As the cloud falls inward under its own weight, it spins faster, the way a skater twirls more quickly when they draw in their arms. As the material gathers, gravity starts to act more evenly. It doesn't care about up or down, doesn't favor left or right. Its pull is the same in every direction, wrapping itself around the forming world like a perfectly even pressure. When that happens, something simple and beautiful emerges: roundness. If gravity could choose a shape with no other forces interfering, it would choose a sphere every time. A shape where every point on the surface is as close as possible to the heart inside. But the moment a world begins to exist, it also begins to spin, and spin gently spoils that perfect ideal. Our own planet is a quiet example. Earth turns once in just under 24 hours, and that turning creates a subtle outward push, strongest along the equator. It's not enough to fling rocks and oceans into space, but it is enough to puff the planet out a little around the middle. So the Earth you live on isn't a perfect ball. It's slightly squashed at the poles and a little wider at the waist, a rounded shape that's been stretched by its own motion. The giant planets tell the same story, only louder. Jupiter, so huge and stormy, spins in less than 10 hours. That dizzying rotation pulls its equator outward so much that the difference between its polar and equatorial diameters is thousands of kilometers. Saturn, made mostly of light gases, spins quickly too, and with such low density that its poles are visibly flattened like a softly pressed ball of dough. Their shapes are gravity and spin arguing in slow motion, neither side fully winning. This quiet pattern doesn't stop with planets. Many stars, too, flatten just a little when they rotate. Some spin so quickly that they bulge dramatically, their equators stretched far from their centers, and on much larger scales, whole galaxies show the same compromise. The Milky Way, which you might imagine as a kind of glowing river in the dark, is really a vast, thin disk of stars and gas. Gravity pulls inward toward the center, while the spin of all those stars keeps them circling in a flattened plane. Once again, the shapes you see are a long-term truce between inward pull and outward motion. As clouds of gas in space fall under their own gravity, they want to become spheres, but because they turn, they're drawn out into disks instead. Within those disks, smaller clumps collapse further into nearly round embryos of planets and moons. Over and over, the universe repeats the same choreography: gather, spin, flatten a little, and then round out again wherever gravity becomes strong enough to smooth things. Roundness is not just skin deep. Gravity works all the way down to the core. Deep inside Earth, layer upon layer of rock and metal is squeezed by the weight above. The pressure in the center rises to millions of times the gentle air pressing on your skin at the surface. That enormous weight keeps everything compact, removing large bumps and hollows over time, pushing the planet toward a stable, rounded shape. Inside Jupiter, the crush is even more extreme, turning familiar hydrogen gas into a strange, metallic form that can carry electric currents like a liquid metal. Even there, in conditions you and I can hardly imagine, gravity is still insisting on symmetry. There is a quiet rule hidden inside all of this. The bigger an object gets, the more its own gravity starts to win over the toughness of its material. A small rock in space can be jagged, lumpy, shaped by chance collisions and cracks. But as its size grows, its own weight begins to pull those irregularities down. Beyond a certain size, the stone can no longer hold its sharp edges. It softens into a nearly round world. When a body is a few hundred kilometers across or more, its gravity usually becomes strong enough to smooth it into a sphere or something very close. That's why some large objects in the asteroid belt look like tiny planets, while their smaller neighbors still resemble misshapen rubble. The universe, in its quiet way, doesn't seem to like imbalance. Extra bumps, sharp corners, uneven piles of material given enough time. Gravity will gently tug at them, redistributing mass until things even out. The larger the object, the more insistently this happens. The smaller it is, the more it can resist, clinging to its odd shapes and sharp edges. Every world you can name, from the tiniest round dwarf planet to the largest star, carries a memory of this long, patient conversation between shape and weight. Even the most extreme objects we know follow the same basic logic, just driven to frightening intensities. Neutron stars, the collapsed cores of massive stars, are so dense that a teaspoon of their material would outweigh mountains. Some of them, called pulsars, spin hundreds of times every second. Their equators race around at a significant fraction of the speed of light. At those speeds, the outward push from rotation and the inward pull of gravity are nearly tearing at each other. Matter squeezes, deforms, time itself slows. Yet somehow, a kind of balance still holds. The star does not fly apart. It does not collapse completely into something smaller. It vibrates on the edge of what physics will allow. Everywhere you look, if you could pause the chaos and trace the outlines carefully, the same message would be hiding in the curves. Nothing is completely still, but everything is quietly seeking symmetry. A droplet of water released inside a space station, free from up and down, gathers itself into a nearly perfect sphere. A new planet, battered by collisions and violence, slowly rounds out as its own gravity heals its scars. Even the emptiest-looking regions of space become threaded with clouds and clusters that curve and swirl in familiar patterns. Astronomers, with their patient instruments, keep mapping these shapes. They survey planets and moons, stars and galaxies. They measure how light bends, how matter falls, how orbits trace their invisible tracks. And again, even in places where chaos once seemed to rule, a calm geometry appears underneath. Circles, ellipses, spheres, spirals, roundness, it seems, is the universe's favorite way of answering the question of how to stay balanced while everything is moving. Hidden inside all of that is a deeper mystery. If gravity can shape droplets and planets, stars and galaxies, what happens when it folds space itself? What shape does roundness take when it's no longer just rock or gas being pulled inward, but the fabric of space and time? That question leads to some of the strangest objects the universe has to offer, and to some of the most perfect circles we've ever seen. At the center of our own galaxy, far beyond the soft glow of the Milky Way you might glimpse on a dark night, there is something so heavy and so dense that not even light can escape it. We call it a supermassive black hole, and astronomers have given this particular one a name: Sagittarius A*. It holds millions of times the mass of our Sun, compressed into a region smaller than the orbit of Mercury, and it sits about 26,000 light-years away in the direction of the constellation Sagittarius. To human eyes, and even to most telescopes, it is invisible, swallowed by its own gravity. But in 2022, after years of patient work, a network of radio telescopes spread across Earth came together to create a kind of planet-sized eye. It gathered the whispers of radio waves from around that hidden object and combined them into a single picture, a faint, glowing ring with a dark center. That ring is not the black hole itself, but the light from hot gas swirling around it, bent and trapped by its gravity. The dark middle is the shadow, a silhouette cast by the black hole against that glowing backdrop. In that image, you are not seeing a solid surface. You're seeing space-time itself, curved into a nearly perfect circle. In Einstein's equations, a black hole that doesn't spin is a very simple thing. It is completely described by its mass, and the region around it where nothing can escape is a perfect sphere. The boundary of that region is called the event horizon. Cross it, and all paths lead inward. Time and space change roles, and every possible future takes you deeper, never back out. The radius of this invisible sphere grows with the black hole's mass, but its shape stays the same: round, even, symmetrical in every direction. Out in the real universe, though, nothing stays perfectly still. Stars spin before they die, and when they collapse into black holes, that spin doesn't just disappear. It's squeezed and concentrated, just like the star's mass. The result is a rotating black hole, one where the event horizon is no longer a perfectly simple sphere, but slightly flattened at the poles and stretched at the equator, much like a planet. Around it, space itself is dragged into motion, twisted by the rotation. There is a region where nothing can stand still, where even light is forced to swirl around before it can hope to escape. It's as if the black hole's spin has tangled the fabric of reality into a gentle spiral. We've seen hints of this spinning behavior in other galaxies too. At the center of a giant galaxy far away, astronomers have watched enormous jets of material streaming out along the black hole's poles, stretching thousands of light years into space. The best explanation we have is that these jets are powered by the black hole's rotation, somehow tapping into its stored spin and flinging energy outward along invisible magnetic fields. You can almost imagine the black hole as a kind of cosmic flywheel, its rotation shaping the fate of stars and gas in an entire galaxy. And yet, even with all that motion and power, the outline we see when we look at a black hole's shadow remains astonishingly round. The same Earth-sized telescope network that imaged Sagittarius A times also captured the black hole in that distant galaxy. In both cases, the dark center was almost a perfect circle, its edges only slightly distorted. According to our best tests so far, the geometry predicted by Einstein still holds, even when spin twists and stretches the surrounding space. The shadow that reaches our eyes stays remarkably close to a simple ring. There is something deeply unsettling and beautiful about that. A black hole has no surface we can touch, no mountains, no craters, no scars carried from its past. As far as our equations can tell, it is defined only by a few numbers: how much mass it has, how fast it spins, and whether it carries any electric charge. Everything else about the star or cloud that formed it, the details, the messiness, the history, disappears behind the horizon. What remains is an almost pure shape, an object whose identity is geometry. We've even heard the echoes of these shapes in the form of gravitational waves, tiny ripples in space-time that roll past Earth when black holes collide. When two of these dark spheres spiral together and merge, the disturbance they send across the universe is one of the most violent events we can imagine. And yet, as the new black hole settles down, the waves fade in a way that matches a simple picture: a distorted sphere gently ringing like a bell, then relaxing back into a stable, rounded form. Some of the largest black holes we've measured seem to spin astonishingly fast, carrying almost as much rotation as the laws of physics will allow. Their spin stirs the gas around them, lights up space in X-rays and radio waves, and can influence how stars form in the galaxy around them. If they could spin just a little faster than the limit, our equations suggest that their horizons might break open, exposing the singularity inside. But so far, nature has given us no sign of such naked extremes. The horizons seem to hold, bulging a little at the equator, but never tearing. Astronomers sometimes call black holes laboratories of gravity, not because we built them, but because they push gravity into regimes we could never create on our own. They show us what happens when mass and energy bend space-time to its limits. Every photon that grazes their edges, every orbit that skirts their shadows, every gravitational wave from their collisions carries information about how the universe behaves when the rules are stretched to their edge. In physics, symmetry is not decoration. It's a sign that something deep is being conserved, that the laws are the same no matter which direction you turn or where you choose to stand. The nearly spherical shape associated with a quiet, non-spinning black hole reflects a profound symmetry. The idea that space behaves the same in every direction. That same idea lies behind the way gravity pulls equally from all sides, behind the way roundness keeps appearing in planets and stars and droplets. Yet the moment you bring motion into the picture, that pure symmetry bends. Spin doesn't destroy it, it reshapes it, twisting circles into spirals, flattening spheres into gentle bulges. The universe itself seems to follow this pattern, expanding and curving on the largest scales, perhaps even carrying a slow, global rotation we are only beginning to test. Still, under the flow and change, the same preference for balance keeps whispering through. Black holes sit at the crossroads of all these themes. They are born in violence, yet described by simplicity. They are places where our current understanding of physics thins and frays, and still, the outlines we can see are calm and almost perfectly round. They tell us, in their own silent way, that even in the most extreme corners of reality, the urge towards symmetry has not been completely lost. Even black holes, the most extreme structures in existence, are ruled by symmetry. If black holes are the most intense, concentrated expressions of gravity's love of roundness, galaxies are that same story told on an enormous, delicate canvas. Instead of a single dark circle, you get wide, glowing whirlpools of stars. And yet, when you look at them in photographs, they don't seem round at all. They're thin, bright disks, like someone has pressed the universe flat in those places. If gravity is so fond of spheres, why did the Milky Way become a disk? To trace that answer, you have to go back to a time before there were stars, when there was only a vast, dim cloud. Long ago, our galaxy began as an enormous, nearly invisible mixture of hydrogen, helium, and a little dark matter, all spread out and slowly pulling itself together. Even then, there was almost certainly a tiny bit of spin, just the faintest turning, barely noticeable on such a huge scale. But in the quiet mathematics of the cosmos, even barely is enough. As the cloud started to collapse under its own weight, that slight spin couldn't just disappear. The same rule that makes a skater spin faster as they pull in their arms applies to whole galaxies. As the cloud shrank, its rotation sped up. What began as a slow swirl became a faster one, and then faster still. Over millions of years, the cloud didn't just fall inward, it spread outward in a circle, like dough spinning beneath a baker's hands, thinning into a disk. Inside this turning cloud, gas and dust grains weren't peaceful. They bumped, brushed, and collided. Each small collision was like a tiny negotiation. Cancel a bit of motion up and down, keep most of the motion around and around. With time, those countless encounters took away the movements that tried to escape the plane of rotation and left behind the motion that lay along it. Slowly, the cloud settled into a thin, rotating sheet to the galactic disk. Our Milky Way is the quiet result of all that drama stretched over billions of years. From above, it would look like a bright, spiraling pattern of stars and clouds, maybe a little barred structure across its center. From the side, it would hardly look like anything at all, just a narrow band of light, only about 1,000 light years thick, compared to its enormous width of roughly 100,000 light years. If you imagined the galaxy as a dinner plate, its thickness would be no more than a smear of light, and our sun would be a tiny speck of dust near the edge. Gravity didn't vanish when the disk formed. It simply changed how it acted. Instead of pulling everything toward a central point in all directions equally, gravity began to cooperate with the galaxy's spin. Stars and gas clouds orbit the galactic center at high speeds, their paths curved by gravity, but held in motion by their inherited spin. The balance point between falling inward and flying outward is a circular orbit, and together, billions of those orbits trace out the flat disk we see. But the disk isn't the whole story. Wrapped around it, like a faint, invisible cocoon, is a vast halo of dark matter, a roughly spherical cloud of something that doesn't shine, doesn't glow, but still has weight. That hidden halo is the quiet reminder that gravity still prefers roundness. It holds the galaxy together from the outside, providing most of the pull that keeps stars in their orbits, especially far from the center. Without that unseen sphere of mass, the Milky Way's outer parts would spin themselves loose. Closer in, near the center, things look different again. There, the speeds and directions of stars grow more tangled. Gravity dominates more strongly than the graceful order of the disk. The result is a bulge, a round, thick cluster of stars swelling out above and below the main plane. At the very heart of that bulge lies the supermassive black hole we visited before, Sagittarius A*, anchoring the innermost region in the deepest gravity well of all. So the Milky Way is not simply flat and not simply round. It is both a spherical dark halo, a rounded central bulge, and a thin spinning disk threaded with spiral arms. At different distances from the center, different aspects of the same laws take charge. Near the core, gravity sculpts something more spherical. Farther out, rotation stretches matter into a plane. Between the two, you get the hybrid shapes that fill astronomy textbooks and night sky photographs. Other galaxies tell similar stories in their own dialects. Some, like our neighbor Andromeda, wear their spiral disks proudly, arms sweeping outward in delicate curves. Others are more puffed out and oval, with little sign of a thin disk. These are the ellipticals, where rotation plays a smaller role and gravity gathers stars into a more rounded form. Many dwarfs are lopsided and irregular, shaped by tides and collisions, and still in the process of settling. Underneath their differences, though, the same themes repeat. Spin flattens, gravity rounds, and together they decide which shapes are stable over cosmic time. The disk of the Milky Way isn't frozen. It flexes and ripples, stirred by passing satellite galaxies and currents of dark matter. Measurements of star motions reveal waves in the disk, like a sheet of fabric that's been gently shaken. Our galaxy, for all its majesty, is still ringing from old encounters, still adjusting its balance. Far away, Andromeda is drifting toward us, carrying its own disk and bulge and halo. In several billion years, the two will meet and merge, their spins and masses combining into a single, larger system, probably rounder, slower, more like an enormous elliptical galaxy than the thin spirals we know now. Even on that scale, when rotation cancels out and energy is redistributed, roundness quietly returns. All of this invites an even larger question, one that sits underneath everything else. If droplets become round, planets become roundish, stars become round, and even galaxies and halos find their compromises between flat and spherical, then what about the universe itself? Does all of space have a shape? When we talk about that shape, we're not asking about the outline of the visible galaxies, but about the geometry of space itself, the way distances and angles behave over unimaginably large scales. If you heard that the universe began as something like an explosion, you might picture a ball of fire expanding into emptiness, a growing bubble with a curved surface. But when scientists point their instruments at the oldest light, they can see the faint afterglow of the Big Bang. They find something subtler. That ancient light, stretched into microwaves by nearly 14 billion years of expansion, carries tiny variations in temperature, little speckles of slightly hotter and cooler regions. Those speckles are like fossil fingerprints of an infant universe, where matter was denser, where it was thinner, how clumpy things were allowed to be. By measuring the patterns of those variations across the sky and comparing them with the predictions of our theories, researchers can infer whether space, on the largest scales we can observe, curves like a sphere, dips like a saddle, or lies flat. So far, The answer they keep finding is almost eerily precise. Flat. Not flat like a sheet of paper, but flat in the sense that the familiar rules of geometry still hold, even across tens of billions of light years. Parallel beams of light remain parallel. Huge triangles drawn between far-flung galaxies would have angles adding up to 180 degrees, just as your school geometry promised. If the universe has any overall curvature at all, it's so small that our best measurements can barely detect it. And yet, that very neatness is what bothers some of the people who study it. Gravity, after all, is supposed to curve space wherever there is mass or energy, and the universe is full of both. Galaxies, clusters, dark matter, radiation, all of them are constantly bending the fabric they inhabit. How, then, can the overall structure of that fabric appear so perfectly balanced between curving inward and curving outward? One of the ideas that may explain this is called inflation. It suggests that in the earliest sliver of a second after the Big Bang, the universe expanded at a staggering, almost unimaginable rate, doubling in size again and again in an eye blink. This rapid stretching would have taken any initial curvature and smoothed it out, much as blowing up a balloon makes any small patch of its surface look flatter and flatter. From our perspective, inside one tiny region of this vastly enlarged space, things would appear flat because the true curve is spread over a scale far beyond what we can see. Our observable universe, the part we can in principle receive light from, is like a small circle of lamplight in a dark field. Beyond that circle lies more field, perhaps with hills and valleys, but the patch we see feels level beneath our feet. When satellites map the cosmic microwave background and find flatness, they're really saying, within our circle of lamplight, space behaves as though it's not curved much at all. The story becomes more tangled when we add dark energy, the mysterious something that seems to be speeding up the expansion of space today. Its presence means that distant galaxies are not just drifting away from us, they're receding faster and faster as time goes on. If dark energy changes its behavior over cosmic history, the overall geometry of the universe could shift subtly too, tilting from one kind of balance to another. For now, the data still whisper, flat, but with a softness that leaves room for surprises. Other observations add their own hints: the way galaxies cluster, the way gravitational waves travel, the way light from distant supernovae grows dim. All of these depend sensitively on the curvature of space. So far, they line up with the same picture. If the universe curves at all on the largest scales we can probe, it does so only very gently. But measurements always come with margins, tiny uncertainties that leave space for possibilities just beyond the edge of our reach. There are models in which our flat-looking universe is just a patch on something larger and curved, a higher dimensional shape that we can't see in full. In those ideas, space might be finite but unbounded, like the surface of a globe, in more dimensions than we can directly perceive. You could travel in what feels like a straight line forever and perhaps, after an unimaginable journey, return to where you started without ever encountering an edge. As our telescopes grow sharper and our detectors more sensitive, they sometimes uncover details that push us back into mystery. We find huge, mature galaxies already present when the universe was very young. We see structures and alignments that are hard to fit neatly into our existing models. Each new discovery is like turning up the brightness on a dim picture. The more clearly we see, the more texture appears, and the harder it is to pretend the story is simple. So when we say the universe is flat, we're really saying within the part we can study. The rules of geometry look very close to the ones we know. Beyond that, the truth could be stranger. Space might curve gently back on itself. It might stretch into shapes we don't have good words for yet. Our flatness could be local, temporary, or only an approximation, like mistaking the sea for featureless until you learn to read the waves. Some scientists have put it this way: the universe is not required to match our favorite pictures. It isn't obliged to be a sphere or a plane, just because those are the shapes that sit most comfortably in our minds. The cosmos can be flat, curved, both, or something that makes those words feel too small. Our measurements draw a careful boundary around what we currently understand. Beyond that boundary, space might not just bend distance, it might bend what we mean by shape at all. And if that's true, if our whole visible universe is only one small, gently curved patch of a deeper reality, then the word flat becomes less like a verdict and more like a soft, provisional guess, a placeholder for something we don't yet have language for. It could be that what we call flatness was never real to begin with, only the way a limited view feels from where we're standing. If flatness is an illusion, it may be because we're always looking from too close. Every line we trust, every straight road, every calm horizon might just be a tiny patch on something vast and gently curved, a bend so wide that, from where we stand, it feels perfectly level. We name things from inside that smallness. We say planets are round, galaxies are flat, space is infinite. But those are the words of creatures tied to a single world, peering out with limited reach. From a higher dimension, even the thinnest spiral galaxy might be part of a gigantic curve, looping back on itself over distances so huge that no light has had time to show us the bend. What feels like an endless, straight path might really be a closed track, and we're too small to notice we're going in circles. This isn't just late-night daydreaming. Some analyses of data from the Planck satellite have suggested that the universe might be ever so slightly curved, shaped like a huge hypersphere, a four-dimensional cousin of a ball. In such a space, you could set off in what feels like a straight line and, given inconceivable time and distance, eventually come back to where you began without ever turning. Einstein's picture of gravity sits quietly beneath all this. In his view, gravity isn't a mysterious pull acting across empty space. It is the shape of space warped by mass and energy. Matter tells space how to curve. Space tells matter how to move. On small scales, that curvature makes planets orbit, light bend, and time tick differently near massive bodies. On the largest scales, it sets the overall geometry of the cosmos. There's a simple balance hidden in the math. If the total density of the universe sits at a certain critical value, space is flat. Above that, gravity curves the whole cosmos inward, like the surface of a sphere. Below it, space curves outward, like a saddle. Our best measurements say we live extremely close to that critical line. But close may not mean exact. The universe could have a radius of curvature so enormous that even across all we can see, the deviation from flatness is too gentle to notice. It's like standing on Earth without a map. Under your feet, the ground feels flat. The horizon looks like a straight edge. Only when you can step far enough back, far beyond human scales, does the global curve become obvious. Space may be doing something similar. It might be curving softly all around us, but on a scale so huge that our entire observable universe is just one small, almost flat patch on a much larger shape. The oldest light we can see, the cosmic microwave background, carries hints of this deeper geometry. Its tiny temperature ripples aren't perfectly uniform. There are odd regions and subtle alignments that don't fit a perfectly simple flat picture. On their way to us, those ancient photons don't travel along pure straight lines. They pass through clusters of galaxies, through invisible clouds of dark matter, skimming the edges of voids. Each encounter bends them slightly. This gentle, weaving gravitational lensing distorts the pattern in ways that whisper about the hidden curvature underneath. Some theories go further and imagine that our universe is like a three-dimensional sheet, a brain, floating in a higher dimensional space. In those ideas, part of gravity's weakness comes from the fact that it can leak into the extra dimensions, while light and ordinary matter are mostly trapped on our brain. Experiments at particle colliders have hunted for tiny hints that energy is vanishing into unseen directions. They haven't found clear signs yet, which means if those extra dimensions exist, they're very small or very shy. Still, the math allows a picture where our apparently flat world is actually a flexible sheet, curled and folded in ways we cannot feel directly. In that picture, a galaxy like the Milky Way could sit on a patch of space that feels flat to everything inside it, while the patch itself curves as part of a larger whole. Just as you can roll a sheet of paper into a tube without stretching the paper, local flatness can live happily inside global curvature. This is one of the quiet lessons of relativity. Space can be locally flat and globally curved at the same time. The flatness we measure is always tied to how far we're able to look. Even within the observable universe, shape changes with scale. The solar system looks almost flat because the planets share a common orbital plane, a memory of the disk from which they formed. The Milky Way looks flat from the side because its stars, gas, and dust have settled into a thin, rotating layer. But when you zoom out to see clusters and superclusters, intertwined filaments and yawning voids, that neat flatness dissolves into a lumpy, foamy web. Gravity pulls matter into threads and knots. Dark energy stretches the spaces between. Straight lines start to feel like approximations laid across a restless fabric. To probe the geometry more precisely, astronomers use patterns left over from sound waves in the early universe. Before space was transparent, matter and light moved together as a hot, vibrating soup. Waves of compression rippled through it, leaving a preferred scale in how matter clumped. Today, that preference shows up as a faint echo in the spacing of galaxies. By measuring how that echo looks at different distances, scientists infer how space has expanded and whether it curves. So far, those measurements agree with a universe that is very, very close to flat, though tiny departures are still possible within the uncertainties. If space does curve in some subtle way, it would touch almost everything about our cosmic story. How dark energy behaves, how fast galaxies separate, whether expansion continues forever or takes some unexpected turn. A perfectly flat universe being pushed outward by dark energy seems destined to grow colder and more dilute. A universe with more positive curvature might one day slow and recollapse. A universe with negative curvature might expand forever, but in a way that gradually isolates distant regions from each other. Each of these possibilities leaves a different faint signature in the oldest light. Beneath all this lies another kind of geometry, one that doesn't live in ordinary space, but in the space of possibilities. Quantum mechanics describes particles not as tiny marbles, but as spread out waves of chance. Their behavior is governed by patterns that curve and interfere in an abstract space of states. Some researchers suspect that the shape of actual space-time might emerge from these deeper quantum relationships, that what we call flatness or curvature could be large-scale illusions built from more fundamental, invisible structures. If that's true, geometry is not the stage, but a pattern that appears when many smaller stories are woven together. Carl Sagan once described Earth as a mote of dust suspended in a sunbeam. If he could see the maps we draw now, he might add that our dust mote is riding on a curve so immense that no line we trace can truly be straight. The more precisely we measure the universe, the more we find that geometry, the first simple language we learn in school, hides some of the deepest secrets the cosmos keeps. And yet, amid all these possibilities of hidden curvature, extra dimensions, and emergent space, one simple shape keeps returning like a refrain: the circle, the sphere, the curve that closes on itself. No matter how strange the underlying reality may be, roundness shows up again and again, from droplets to planets, from stars to halos of dark matter. It looks less like a coincidence and more like a habit of the universe. The reason is soft and stubborn. In the emptiness of space, with no air to shove things around and no walls to hold them in, only a few tendencies remain. Forces pull, energy spreads. Over time, everything tries, in its own way, to relax. A sphere is the shape of that relaxation. It's the only form where every point on the surface is as close as it can be to the center, with nothing sticking out or left behind. Among all shapes that enclose the same volume, a sphere has the smallest surface area, the least exposed edge, the calmest boundary. You can watch that principle in miniature. In the weightless environment of a space station, when astronauts release a small blob of water, it doesn't hang there as a cube or a jagged lump. It pulls itself inward. Molecules tug on each other until the drop becomes a nearly perfect sphere. That's surface tension at work, quietly trying to minimize area. Disturb the drop and it quivers, then slowly settles back toward roundness, as if remembering where it's most at ease. Now imagine the same story on a larger scale, with gravity playing the role of surface tension. When a chunk of rock or ice in space grows beyond a certain size, its own gravity starts to pull seriously on every part of it. Peaks slump, deep pits fill, and over long stretches of time, the body rounds itself. Astronomers call the result hydrostatic equilibrium, the state where gravity has won over rigid structure, enough to smooth out the worst irregularities. Larger bodies become worlds, smaller ones stay as boulders in orbit. You can see the difference clearly in our solar system. Ceres, the largest object in the asteroid belt, is big enough that its gravity has made it roughly spherical. Many smaller asteroids still look like fractured stones, elongated or lopsided, because they simply don't have enough mass to pull themselves into roundness. Here, roundness is something that must be earned. Stars follow a related rhythm. As a star like the Sun pulls gas inward with gravity, the heat and pressure from nuclear fusion push outward. When those two tendencies balance, the star settles into an almost perfectly spherical shape. Our Sun is extraordinarily round, so much so that the difference between its equatorial and polar diameters is tiny compared to its overall size. It is, in a very literal sense, one of the roundest things nature has ever made. Spin, however, always nudges symmetry. As soon as something rotates, an outward tendency appears at its equator. That's why Earth bulges a little at the waist and flattens slightly at the poles. Gas giants like Saturn spin so quickly and are so light for their size that the effect is much stronger. Their equators bulge visibly. Even so, from afar, they still read as globes. Their forms are roundness adjusted by motion, not abandoned. Across the galaxy, telescopes that measure star shapes tell the same story. Some stars are a bit squashed by rapid rotation or distorted by the pull of close companions, but left in peace, they tend to drift back toward rounder forms. Roundness is where the arguments stop, where inward and outward come as close to agreement as the conditions allow. At the extreme, roundness becomes pure geometry. A non-spinning black hole in Einstein's equations is a perfect sphere in space-time, defined by a single number, its mass. Add spin, and the symmetry is gently distorted, yet the outline we infer from light and gravitational waves remains eerily circular, as if the universe refuses to let even its strangest objects stray too far from that simple, closed curve. What's most soothing is how universal this pattern is. The same mathematics that describe a water droplet pulling itself into a bead describe a star finding its shape and a cluster of galaxies settling into a roughly spherical halo. From atoms to galaxy clusters, everything seems to be playing variations on the same quiet theme. Given time, given freedom to move and interact, systems drift towards smoother, more symmetric states. On cosmic scales, that smoothing shows up in the halos of dark matter surrounding galaxies, which simulations reveal to be close to spherical, despite all the chaos of mergers and collisions. Those halos cradle the thinner, flatter disks of stars within them, giving them the stability they need to survive. Even the faint microwave glow from the early universe is strikingly uniform, its tiny temperature differences telling us that, from very early on, the cosmos has been nudging itself toward balance. Roundness, then, is more than a pleasing shape. It's a record of forces that have had time to argue and reconcile. It is the geometry of rest, written wherever energy has been allowed to settle. Every round world is a quiet truce between gravity and resistance. Every smooth star a frozen agreement between collapse and pressure. But this soft victory is not universal. There are places where balance falters, where rotation becomes wild and gravity strains to keep up, regions where motion refuses to calm down and roundness begins to fray. What happens to roundness there? What shapes are born when motion refuses to settle? If the universe could tolerate sharpness, the night sky might have looked very different. You could imagine cube-shaped planets tumbling around angular suns, pyramids gliding through space, moons with knife-edged ridges casting perfect triangular shadows. But when we actually look out there, with telescopes and quiet patience, that's not what we see at all. From tiny droplets to giant stars, everything seems to lean towards smoothness. Curves, arcs, halos, no true corners, nothing jagged that lasts. Everywhere you look, the same soft geometry repeats. Spheres, stretched spheres, gentle spirals, rounded clouds. The question isn't only why so many things are round, but why nothing sharp seems to survive for long. The answer, whispered underneath almost everything, is gravity. Not a chisel, not a knife, not a tool that cuts more, like a slow, invisible tide. Every particle feels its pull, and that pull comes equally from all directions. Given time, that evenness wears down whatever tries to stand out. High points slump, deep gaps fill, edges blur. Gravity doesn't like favorites, and it doesn't like imbalance. It just keeps nudging matter toward the shape where every pull is balanced. The sphere. You can see a small version of this on Earth. Mountains rise, continents shift, cliffs crumble, It all looks wild and jagged from where we stand. But if you could wait long enough, far longer than any human lifetime, those peaks and ridges soften. Rock breaks down under its own weight, slides, sinks, washes away. Tectonic plates push and pull. Oceans lap at coasts. Gravity is always working in the background, asking the landscape to smooth itself out. It will never make Earth into a perfect ball, because the crust is stiff and the planet is still restless. But the general tendency is there. Edges don't last. Out in space, where worlds are born, the same rule gets even clearer. When a rocky body is small, its own gravity is weak. It can stay lumpy, cracked, irregular, just a loose pile of stone. That's why so many asteroids look like rubble glued together. But when an object grows to a few hundred kilometers across, its own weight starts to win over the rigidity of rock. Mountains can't stand as tall. Deep hollows can't stay as deep. Slowly, over millions of years, the whole object relaxes into something rounder. Astronomers call that moment hydrostatic equilibrium, when gravity has become strong enough that the natural resting shape is a sphere. Ceres, the largest object in the asteroid belt, is an example of that quiet surrender. It probably started as a chaotic cluster of smaller things, colliding and merging, but over long ages, its gravity pulled everything inward and smoothed the worst irregularities away. Today, beneath its craters and scars, it is essentially a round world. Smaller asteroids nearby still look jagged, as if frozen mid-transition. Some, like the rubble pile Bennu, are especially telling. Not quite a neat sphere, not just a random shard either, but something in between, already starting to feel the pull of that same destiny. Even when you shrink down to the microscopic, the story doesn't really change. A free droplet of water, a tiny bubble of oil, even certain living cells will curl into spheres when they're left alone. There, gravity isn't the main player. Surface tension is. Molecules at the surface tug on each other, and the system tries to minimize the exposed area. Out of all possible shapes that hold the same volume, a sphere has the smallest surface. It is, once again, the most efficient way to rest. Edges and corners, in contrast, are places where something is out of balance. They concentrate stress, they focus forces and differences. A sharp ridge is where gravity, pressure, or tension has not yet had time to even things out. In the language of physics, that means higher energy, a state that is less likely to last. Left on its own, a system will tend toward more even distributions of energy and matter, more uniformity, fewer extremes. Smoothness is not just pretty, it's statistically favored. Inside stars, this preference becomes even more striking. The sun is a roiling, boiling ball of plasma, with temperatures in the core reaching tens of millions of degrees. You might expect that chaos to show up in its shape, yet the immense inward pull of gravity and the outward push of hot gas find a delicate balance from center to surface. That balance holds the star in an almost perfect sphere. The storms, flares, and loops we see on its surface are tiny ripples on that deeper symmetry. Gas giants like Jupiter follow the same pattern. Their atmospheres are full of storms larger than Earth, winds screaming around their equators. But their gravity is so strong that, overall, they stay nearly spherical. Only their rapid spin flattens them a little at the poles, reminding us that motion can stretch symmetry, but only so far before gravity pulls it back toward round. Zoom out again, and you find these curves on grander scales. Galaxies, though they look like delicate disks or soft ovals, are still dominated by smooth gravitational fields. Clusters of galaxies, wrapped in halos of dark matter, show rounded envelopes when you step back far enough. Even the oldest light we can see, the cosmic microwave background, glows with astonishing uniformity. Its temperature varies by only tiny fractions from place to place. There are ripples after all. Structure had to start somewhere. But those ripples are small, sitting on top of a nearly even sea. Part of the reason sharpness is rare comes from simple thermodynamics. Systems tend to evolve toward states where energy is spread out, not clumped. Jagged forms, sharp divides, and steep gradients all mean energy is sitting in an uneven way, ready to flow. Smoothness is what happens when that flow has mostly finished, when no big differences remain to drive change. The second law of thermodynamics, softly interpreted, is a law about how edges get blurred over time. Another reason lies in the mathematics we use to describe the universe. Einstein's equations treat space and time as something that can bend and curve, but they do so smoothly. Real, perfect corners in the fabric of space-time would break those equations. In the models we build, and in the analog experiments we run, fluids spinning in tanks, cold atoms arranged into gently rippling fields, the patterns that emerge under gravity and motion are always continuous waves, never permanent spikes. Edges show up briefly, then relax. We can even watch this smoothing process play out in the most extreme places we know, merging black holes. When two of these objects spiral together, the final moments are messy and asymmetric. The newly formed black hole rings and vibrates, sending gravitational waves across the cosmos. Those waves carry away the irregularities. What's left behind is a calmer, rounder horizon, a sphere of warped space-time, still spinning perhaps, but stripped of the worst distortions. It's like listening to a struck bell fade into a single pure tone. All of this makes sharpness feel less like something the universe hates and more like something it simply cannot maintain. Edges are temporary. Ridges are temporary. Corners are temporary. Curves are what remain after time, and gravity have done their quiet work. You and I can build cubes and pyramids, make structures full of angles and lines, but those shapes survive only as long as stronger forces hold them together. The universe itself, left to its own devices, writes in arcs and spheres. At the heart of this soft insistence is gravity, acting not like a sculptor with tools, but like the shape of the stage itself. In Einstein's view, gravity is not a separate force pushing or pulling from a distance. It's the way mass and energy curve space-time, the way the fabric of reality bends in response to whatever sits on it. Place something heavy on that fabric, and it makes a well. Put smaller things nearby, and they slide along the curves, not because they're being yanked by invisible strings, but because straight paths have changed. On small scales, surface tension and other forces can compete with gravity, sometimes even dominate. On larger scales, gravity quietly takes over. A drifting cloud of gas becomes a star because gravity pulls it inward until fusion lights in its core. A cluster of rocks and ice turns into a planet when gravity grows strong enough to overcome their stiffness and round them. A massive star dies and collapses into a black hole when gravity outmatches every other push that could resist it. In each case, the end shape is defined more by geometry than by material. A sphere for a planet, a nearly perfect sphere for a calm star, a spherical horizon for a quiet black hole. Even when things are disturbed by magnetic fields, by explosions, by collisions, gravity plays the long game. Supernova blasts can leave jagged shells of gas, twisted knots of plasma, but as that hot matter cools, The scattered pieces fall back into the slow choreography of orbits and collapse. Over time, the wreckage becomes part of new stars, new planets, new round worlds. The moon, for example, bears the scars of countless impacts, each one a moment of violence. Yet beneath that cratered surface, its overall shape is still that of a sphere, held in place by its own mass and gravity. In this sense, gravity is both creator and editor. It gathers, shapes, smooths, and endlessly revises. It doesn't erase all detail. Mountains still stand, rings still circle, spiral arms still unfurl, but it sets the broad boundary conditions. It decides that on large enough scales, and after enough time, edges will soften and roundness will dominate. There is, however, another presence in this story that never really goes away. Motion, spin, drift, orbit, turbulence, all the ways matter can refuse to sit perfectly still. Gravity can tame many of these motions, but not all of them completely. Rotation, especially, is stubborn. It flattens stars slightly, puffs out planets at their equators, stretches galaxies into thin disks. It takes the sphere, the favored shape of balance, and gently distorts it, sometimes almost to the breaking point. Most of the time, gravity holds its ground, and the compromise looks peaceful enough. A slightly squashed planet, a star that bulges a little, a galaxy shaped like a glowing pinwheel. But there are regions in the universe where motion pushes much harder, where rotation becomes so fierce that gravity starts to strain. And that brings us back to the question, forming quietly at the edge of all this. What happens when motion pushes back so strongly that gravity begins to lose control? What new shapes appear when balance itself starts to bend? When you think about how stubborn roundness is, it can be comforting to look at something small and familiar, not a star or a planet, but a soap bubble. Imagine bending a piece of wire into a triangle, or a square, or a little star. You dip it into soapy water, lift it carefully, and for a moment, the thin film stretches across your chosen shape. It looks like you've convinced nature to play along with your angles. But the moment you blow a bubble from that frame and let it drift free, the pretense vanishes. The bubble shrugs off your triangle, forgets your square, and curls itself into a sphere. Corners vanish, edges melt. The bubble becomes what it wanted to be all along. Inside that tiny, weightless globe, the same logic is at work that shapes worlds. On the surface of the bubble, molecules of water and soap are pulling on each other. Surface tension is their quiet agreement. Keep the surface as small as possible. Share the strain evenly. For a given amount of air inside, there is only one shape that lets every point on the surface feel the same gentle pull and exposes the least area to the outside, a sphere. Anything else would mean some patches are more stretched, more stressed, more uncomfortable than others. So, even though your wire can be any shape, the film it holds will always try to find what mathematicians call a minimal surface, the smoothest possible form that fits the boundaries it's given. If you trap soap films between wires, you get beautiful curved sheets arching and twisting in space, never quite flat, always bending just enough to share the tension. But the moment the film closes on itself, without any rigid frame to constrain it, the answer is always the same: round. Look more closely, and the bubble becomes even more of a tiny cosmos. Its skin is just a few hundred nanometers thick water sandwiched between layers of soap molecules, each molecule with one end that loves water and one that tries to turn away from it. As you blow air in, pressure inside the bubble pushes outward, Surface tension pulls back. The bubble grows until those two tendencies come into balance, and then it stops. Outward and inward equalize, and a little sphere floats in the air, held together by that quiet contract. In weightless environments, like a space station orbiting Earth, you can see this even more clearly. Without gravity pulling liquid down, drops of water drift like tiny, glimmering planets. Nudge them and they wobble, but they keep returning to the same rounded form, trying to distribute tension evenly. One astronaut once joked that in microgravity, water behaves as if it wants to be a world, and in a way it does. It's following the same rule. Minimize energy, maximize balance. Even the colors sliding across a bubble's surface are part of the story. Light waves reflecting from the inner and outer surfaces of the film interfere with each other, sometimes adding, sometimes canceling. That interference creates swirls of color that change as the film's thickness shifts. You're watching physics paint with light, every shade a sign of how the bubble is draining, thinning, redistributing its tiny supply of liquid in search of equilibrium. If two droplets meet in that weightless air, they don't stay separate for long. Surface tension pulls them together, smoothing their combined outline into a single, larger sphere. Extra surface area disappears. Extra energy is released as a shiver, a tiny vibration. On a much larger scale, the same thing happens when galaxies merge, when clouds of gas join to form stars, when bits of rock accrete into planets, many become one. Complexity simplifies into a shape that stores the most with the least. This is why you can't make a stable triangular bubble, no matter how much you might want to. Edges and corners concentrate tension. The molecules near them are more strained than the ones in the middle. A triangular bubble would be a bundle of tiny imbalances, each one pushing to be smoothed away. So the film caves in, curves, and erases the angle. Nature isn't being stubborn, it's being efficient. Any configuration that keeps stress sharply focused is a temporary state, a problem waiting to be solved. Curves are the solution. The same idea spills into places that seem very far from playtime with soap and water. Minimal surfaces, those shapes that use the least area to bridge a given boundary, show up in architecture, in the folding of biological membranes, in mathematical theories about how fields and forces arrange themselves. The equations that describe how a soap film hangs between wires also describe, in more complex form, how matter and energy might drape themselves through the curvature of space-time. Simple, soft shapes at the sink echo grand structures in the sky. Bubbles don't live forever, though. As time passes, gravity and evaporation drain liquid from the film, thinning it until it can no longer resist the pressure difference between inside and outside. Then, in a quick, almost soundless moment, the bubble bursts. High-speed cameras show the rim pulling back at surprising speed, the film rolling in on itself as surface tension reclaims the material. Even that ending follows clear rules. A pattern carried as far as it can go gives way to another, and the system moves to a new kind of balance. In a gentle way, a soap bubble is the universe in miniature, atoms, forces, energy, geometry, all cooperating to produce something that looks simple but is quietly profound. To get one small, floating sphere, you need an entire set of laws working together. And those same laws, scaled up, explain why planets and stars and many other things end up round as well. Underneath it all lies a question that keeps returning in different clothing. If you want to hold as much as possible, with as little boundary as possible, What shape do you choose? Over and over, nature gives the same answer: the sphere. Among all shapes, the sphere encloses the largest volume for the smallest surface area. It's an old result in geometry, sometimes called the isoperimetric principle. You could think of it this way: if you have a certain amount of wall to use, and you want to build a container that holds as much as possible, making it spherical gives you the most interior for the least exterior. Less exposed area means fewer chances for heat to leak out, fewer places for stress to build up, fewer imbalances to worry about. Physics quietly leans into that efficiency. Systems that can rearrange themselves will often drift toward configurations that require less energy to maintain. Extra surface area usually means extra energy stored in fields or forces at the boundary. Edges, faces, and corners are places where something is being held in tension. So when molecules, grains of dust, or clouds of gas are free to move and interact over time, they tend to settle into shapes with fewer such places, the shapes that make the job easiest. Take again that droplet in microgravity. Its surface is made of molecules that prefer to stay together rather than stretch apart. If the droplet is misshapen, there are regions where the surface is more heavily strained. Those regions pull a little harder, tugging the shape toward one where the strain is shared more evenly. The droplet doesn't decide to become round. It simply follows countless small pushes and pulls that add up to roundness being the most likely end state. Now blow that scene up in your mind until the droplet is the size of a mountain. Imagine that instead of surface tension, gravity is the main force at work. As you pile more rock or ice onto that body, its own weight begins to matter in a new way. High ridges press down, deep holes feel stronger upward pulls, and the material slowly flows, creeps, or fractures in ways that reduce those extremes. When the body is large enough, its gravity overwhelms the rigidity of the stuff it's made from. It stops behaving like a sculpture and starts behaving like a self-shaping fluid. The result, once again, is a sphere, or something very close to it. Planetary scientists use this behavior as one of the tests for what counts as a world. When an object is massive enough that its self-gravity pulls it into a round shape, they say it has reached hydrostatic equilibrium. That condition marks a kind of threshold. Below it, you have rubble piles, shards, fragments. Above it, you have planets and dwarf planets, places where roundness has been more or less enforced. Stars obey a similar economy of shape. Deep in their interiors, immense pressure from hot gas pushes outward. Gravity pulls inward with equal insistence. Where those two influences balance, a stable star is born. The simplest way for that balance to hold at every angle is for the star to be nearly spherical. Rotation and magnetism can distort the outline a bit, but the underlying tendency is still toward a shape where every direction from the center looks much the same. Even in human engineering, we rediscover this preference. Tanks that need to hold high-pressure gas or liquids safely are often made spherical, or nearly so, because round containers spread stress evenly. Eggs, cells, many seeds and fruits all use more rounded forms to enclose volume efficiently and resist collapse. We imitate a rule the universe has been using since its earliest days. On still larger scales, that same rule is hiding in the background of cosmic structure. When dark matter began to clump in the early universe, it gathered into roughly spherical halos regions, where its own gravity pulled it inward from all directions. Those halos became wells where gas could collect and cool, eventually forming galaxies inside. The galaxies might spin themselves into flat disks, but their invisible halos remain more round, providing the gravitational support that keeps the disks from flying apart. Underneath thin, bright structures, there is often a round scaffold. Mathematically, this preference doesn't stop at 3 dimensions. If you ask in higher dimensional spaces, what shape encloses the most volume for a given surface, the answer is still the generalized sphere, a hypersphere. So even in theoretical worlds with more dimensions than we can picture, the same marriage of efficiency and symmetry holds. The sphere, or its higher dimensional cousin, is the quiet winner. From this perspective, roundness stops feeling like a coincidence and starts looking like a signature. When energy has had time to spread out, when forces have had time to argue and compromise, when things are allowed to rest as much as their surroundings permit, the shapes that emerge are nearly always curved, and the most relaxed of those curves is the sphere. It's the end point the equations keep wandering back to, the form that says, there is no simpler way to arrange this. Astronomers sometimes talk about roundness as a kind of peace. A planet that has become round is one that has settled some of its early violence. A star with a stable, spherical shape is one that has found a long-lived balance between collapse and explosion. Roundness is a sign that, at least for now, the wild motions are being held in check. But even this gentle perfection has its limits. Spin faster and faster, and a sphere starts to bulge at the equator. Stress the inner balance with extreme densities or fields, and new, stranger configurations begin to whisper at the edge of possibility. There are places in the universe where rotation, magnetism, and quantum rules push matter past the comfort zone of simple shapes. If the sphere is nature's favorite solution, what happens when that solution starts to crack? When motion and other forces push beyond balance, does the universe still find symmetry, or does it have to invent entirely new shapes? On a cold morning, if you ever notice a pigeon sitting on a wire, puffed into a fat little ball of feathers, you're quietly watching the same geometry that shapes planets and stars. In the chill, heat turns into something precious. Any warm body has to keep a balance between what it can make inside and what it loses to the outside. How fast that warmth leaks away depends not just on temperature, but on shape. A body with lots of surface compared to its volume bleeds heat quickly. A body that tucks itself into something compact, with less surface for the same volume, keeps its warmth longer. Among all shapes, a sphere is the champion at that game. So when a pigeon fluffs up, it isn't trying to look cute. It's thickening its outline, trapping a layer of air in its feathers. That trapped air is a simple, effective blanket. It slows the flow of heat from the bird's warm core into the colder air, the same way a planet's atmosphere slows the escape of warmth from the ground into space. Seen from far enough away, that pigeon has turned itself into a little sphere of insulation. Other creatures follow the same quiet rule. Arctic foxes curl into tight balls, tucking legs and nose under fur to hide bare skin. Penguins crowd together until they form something close to a single round mass, taking turns at the freezing edges. Seals fold their fins beneath them. Polar bears grow shorter ears and stubbier limbs than their warmer cousins, reducing how much surface sticks out into the cold. Different lives, the same geometry. Keep volume, lose area. Underneath all of that is a simple idea from thermodynamics. The more surface you expose, the easier it is for heat to escape. The less you expose, the more gently warmth drifts away. Being round is a way of being careful, a way of spending as little energy as possible to stay alive. Biology isn't copying some abstract rule. It's discovering it over and over, in fur and feathers and fat, because the rule works. Planets wear their own version of feathers. Earth's atmosphere wraps the globe in a thin, invisible coat of gas that catches some of the heat rising from the surface and sends it back down. Without that shell, our world would be far colder, its average temperature pinned well below freezing. Gas giants like Jupiter and Saturn carry this to an extreme. Their enormous, spherical blankets of hydrogen and helium trap heat from deep inside, so that they glow with warmth they hardly receive from the distant sunday. Their roundness helps too, spreading radiation evenly, not too fast, not too slow, like a slow breath leaving a sleeping chest. Stars are the most intense example of this balancing act. Inside, nuclear reactions produce staggering amounts of energy. Gravity presses inward with equal determination. The two tendencies, outward radiation, inward pull, settle into a fragile truce. The most natural shape for that truce is a sphere where every direction from the core looks the same and energy can flow outward evenly. The star's roundness is not an ornament. It's part of how it stays stable, how it shines steadily instead of tearing itself apart. You can see the same instinct for compactness all the way down to the microscopic. Some bacteria choose nearly spherical shapes to protect their contents and manage the exchange of nutrients. The ratio of their surface to their volume decides how easily they gain and lose what they need. Physics sets the constraints. Evolution writes to fit between them. Scale the view up again, back to solid worlds. A forming planet, at first, is not a sphere at all. In the young solar system, matter gathered violently. Dust grains clung together. Stones collided. Icy fragments shattered and merged. What came out of that chaos were lumpy bodies, irregular heaps of rock and ice dancing around the newborn Sunday. Many of today's asteroids still look like that, elongated, angular, covered in rubble. These small objects stay jagged because their gravity is too weak to insist on anything else. The strength of their rock or ice resists bending. A boulder on a tiny asteroid can sit at an absurd angle and not slide because there isn't enough weight above it to force it down. Their shapes are a snapshot of collisions frozen in time. But as an object grows more massive, something slowly changes. Its own gravity deepens and spreads, now strong enough to tug on every part of it in a noticeable way. High spots feel more pressure underneath. Low spots are slightly relieved. Over thousands and millions of years, rock that seems solid on human timescales can flow, creep, and rearrange like an unimaginably slow liquid. Sharp edges slump, deep craters soften, the entire body relaxes. Planetary scientists call this process gravitational relaxation, and the condition it leads to hydrostatic equilibrium, the state where a world's own gravity is strong enough to pull it into a rounded form. There's a threshold around a few hundred kilometers across where this begins to take over. Below it, you get misshapen relics. Above it, you start to get planets and dwarf planets, places that are round not because something smoothed them with a tool, but because they could no longer stay any other way. We can see this contrast in real neighbors. One mid-sized object may still wear the ghost of its original irregularity, a little too small for gravity to fully win. Another, a bit larger, is a nearly perfect globe, every ridge and valley pressed into a balanced curve over deep time. The first looks like a shard, the second like a world. Inside, the story goes deeper. As a growing planet pulls more material in, its interior heats up from the energy of impacts, from the slow squeeze of compression, from the decay of radioactive elements. Parts of it soften or melt, heavy metals begin to sink, lighter rocks rise, and the world sorts itself into layers. A dense core, a mantle above, a crust floating on top. This differentiation doesn't just help make the outside round, it sets the stage for magnetic fields, volcanoes, drifting continents, maybe even atmospheres and oceans. Icy moons play the same game with different ingredients. Their surfaces are hard and cold, but under the crust, mixtures of ice and water and salt can flow under pressure. Gravity shapes them into smooth spheres, and tidal forces from their parent planets knead their interiors, keeping hidden oceans liquid. Beneath a cracked, frozen shell, a round world might be quietly warm. All of this pigeons on winter wires, penguins in a blizzard, planets rounding themselves from rubble comes back to the same kind of compromise. Systems try, in their own ways, to hold on to what matters with the least wasted effort. For animals, that what is warmth. For planets and stars, it is structural and thermal balance. For the universe as a whole, it may be something even more abstract, an evenness in the way energy and matter are spread. Roundness keeps appearing as the shape that fits those compromises best. It lets a body stay warm with less loss. It lets a world balance its own weight. It lets a star distribute its light. It shows up anywhere the struggle between inside and outside, between push and pull, has had enough time to settle. But nothing stays settled forever. Creatures uncurl, weather changes, planets keep cooling, stars eventually swell and fade, impacts, tides, and internal stresses disturb whatever peace has been reached. The universe is always nudging its own arrangements, testing the limits of every balance it creates. And so a question waits just beyond the edge of all these curves. If gravity can round rock and ice into planets and shape gas into stars, what happens when it works on matter, even softer on great clouds of gas, or even on light itself? Can it still find the same kind of symmetry there, or does the universe have to invent entirely new shapes? If you could slow time to a crawl and watch the early solar system unfold, you wouldn't see neat planets circling in quiet order. You'd see dust and ice and shattered stone whirling around a young star, a bright disk of chaos. Pebbles would brush past each other. Boulders would collide and shatter. Fragments would clump, fall apart, and clump again. For a long while, everything would be debris. Somewhere inside that storm, though, a few pieces start getting lucky. Tiny grains stick together because of weak electric forces, the same kind that make dust cling to a fingertip or a sweater. Little clumps become bigger clumps. Those grow into chunks the size of hills, then mountains, then small worlds. Astronomers call them planetesimals, the seeds of planets. But at first, they are still just rocks, lumpy, sharp-edged, tumbling endlessly around the Sunday. For millions of years, there are countless of these bodies. They bump, merge, and compete for material. Mass follows mass. The more something weighs, the better it is at pulling more in. Most pieces end their story by crashing into something else and disappearing. A very few grow large enough that something deeper begins to stir inside them. There is a moment spread out over a very long time when a growing body crosses an invisible line. Below that line, it can stay jagged because its material is strong enough to hold its shape. Above it, its own gravity becomes too insistent to ignore. Pressure builds toward the center. High spots feel more weight beneath them, low spots feel less. Under that constant squeeze, rock and ice begin, ever so slowly, to flow. On human timescales, stone feels solid. On planetary timescales, under immense pressure, it behaves like something softer creeping a few centimeters a year, slumping, smoothing. Mountains sink. Rims of old craters round off. The entire outline gradually relaxes. Over tens of millions of years, the body pulls itself toward the one shape where inward pull and internal strength can finally balance in all directions. A sphere, or something very close to it. That is the true birth of a world. Not when it gets air, or water, or life, but the moment its own gravity is strong enough to overcome stiffness and sculpt its bulk into equilibrium. Astronomers give this state a calm name: hydrostatic equilibrium. Underneath the formality is a simple thought. The rock has stopped resisting and started resting in the shape its gravity prefers. You can see this line traced in our own solar system. One mid-sized object remains irregular, its outline still dented and stretched, not quite rounded. Another, slightly larger, has been smoothed into a near-perfect ball. In the asteroid belt, Vesta sits just below the threshold, still noticeably lopsided and scarred. Ceres, a little bigger, has crossed over. Its gravity has softened its profile into something clearly world-like. The first is rubble with ambition. The second is quietly a planet in all but name. Once gravity wins that first argument over shape, a chain of changes begins inside. As material compresses, some of the energy of formation turns into heat. Radioactive elements buried in the rock add more warmth. The interior softens. Heavy metals sink inward to form a core. Lighter silicate rocks rise to form a mantle and crust. The body stops being a solid block and becomes layered with an inner life. On Earth, that early sorting gave us a dense iron core that stirs and flows, generating our magnetic field. That field, in turn, helps shield our atmosphere from the harshest solar particles. Without that deep reorganization, without gravity reorganizing us from the inside out, our planet would be colder, barer, and far less hospitable. Roundness on the outside is the first visible sign of all this hidden architecture starting to take shape. Even the giant planets follow the same script. Before they gathered their thick envelopes of hydrogen and helium, their rocky or icy cores would have already been pressed into rounded forms. The gas arrived later, wrapping those cores in deep, swirling blankets. The essential step, gravity pulling a body into balance, comes early and quietly. Far beyond the orbit of Neptune, this pattern continues in slow motion. Some icy bodies out there are still elongated or peanut-shaped, hints that they never grew massive enough or warm enough inside to fully relax. Others, like Pluto, have clearly made the transition. Their surfaces curve smoothly. Basins, ridges, and mountains sit on top of a deeper symmetry that only gravity can enforce. That brings us to the question that once turned Pluto into a household name. Is being round the thing that makes a planet a planet? For a long time, the word planet was used loosely, changing as our view of the sky sharpened. Bright wanderers against the stars, then worlds orbiting the sun, then specific familiar names we memorized in school. When more and more objects were discovered beyond Neptune, some almost Pluto's-size astronomers realized they needed a clearer definition. One part of that definition feels very physical. A planet should have enough mass that its own gravity pulls it into a nearly round shape. That's the hydrostatic equilibrium we've been whispering about. By that rule, Pluto qualifies. and so do several other distant bodies. Their roundness shows that they've crossed the boundary from fragment to self-contained world. But another part of the modern definition has to do with context. A planet should also dominate its orbit, either clearing away most smaller objects or gathering them into stable patterns it controls. Earth, for example, has swept most of the debris from its path around the Sunday. Jupiter has done the same, though it also holds families of asteroids in special resonant pockets. Pluto, by contrast, swims through the Kuiper Belt, a broad population of icy objects that share its region. It does not outweigh that crowd the way Jupiter outweighs its neighborhood. In that sense, it is a leading member of a swarm, not a ruler of its lane. To capture that difference, astronomers created a second label, dwarf planet, a body that is round under its own gravity, but has not cleared its orbital zone. If you only look at the labels, it can sound like a demotion, but the physics beneath them hasn't changed. New Horizons, the spacecraft that swept past Pluto in 2015, revealed an astonishingly complex world. Plains of slowly convecting nitrogen ice, knife-edged mountains, hazy layers of atmosphere, traces of organic chemistry, painting its surface with subtle colors. By any intuitive sense, Pluto behaves like a true world, changing, evolving, expressing an inner balance between heat and cold. The distinction, then, is less about dignity and more about how we choose to organize our language. Nature doesn't stop at clear boundaries. It gives us continuums. Roundness is one measure, telling us whether a body's own gravity has taken charge of its shape. Orbital clearing is another, telling us how influential that body is compared with its neighbors. Pluto scores high on the first, more modestly on the second, and so it sits at an in-between edge in our human-made categories. Even that edge is starting to blur again. Telescopes keep finding new objects beyond Neptune, some small and irregular, some large enough to be nearly round, some on strange elongated paths that hint at deeper gravitational patterns. There are hints that a much larger, unseen planet might lurk far out in the dark, shepherding these orbits from the shadows. If such a world is confirmed, our picture of the outer solar system will shift once more, and our definitions may soften or stretch to fit what we see. For now, the quiet truth is this: roundness tells us that gravity has done something profound. It has taken a pile of debris and turned it into a coherent whole, with an inside and an outside, with layers and history and, sometimes, weather and maybe oceans. Whether we call that body a planet, a dwarf planet, or something else, its smooth curve against the dark is a sign that chaos has been tamed enough for structure to endure. Somewhere beyond Pluto, in the deep, slow cold, there are surely other icy bodies still growing, still colliding, still inching toward that same invisible line. One day, one of them will quietly become heavy enough to soften. Its jagged outline will begin to yield. Very slowly, over ages, it will round itself into a new, small world, another silent candidate drifting at the edge of the sun's faint light, waiting to be noticed and welcomed into the story. If you want to see what gravity does to something softer than rock, you don't have to look any farther than the Sunday. Through a safe telescope, you're not looking at a solid surface at all, but at a restless ocean of plasma atoms, stripped of their electrons, charged particles tangled in magnetic fields, boiling and bursting and twisting. It's more like watching a star-sized storm than a calm object. And yet, from far away, all that chaos holds itself in one of the simplest shapes there is, a nearly perfect sphere. The reason is the same quiet balance that has been following us all along. Gravity pulls inward on every grain of plasma, always toward the center. Deep inside the core, nuclear fusion pushes outward. As hydrogen is pressed into helium, and a little bit of mass turns into a great deal of energy. Those two tendencies collapse, and expansion lean against each other until they match. When they do, the most natural way to share that balance in every direction at once is a sphere. At the sun's heart, temperatures climb to tens of millions of degrees. There, protons move so fast and so close that they sometimes merge, releasing light that will spend hundreds of thousands of years slowly working its way outward, being absorbed and re-emitted in a kind of brilliant, endless relay. By the time a particular photon finally slips free at the surface and heads towards space, it has forgotten its birthplace completely. 8 minutes later, it might land softly on your hand. All the while, gravity has been holding the whole star together, matching the pressure generated by that fusion. If fusion ever pushed much harder, the core would expand and cool, slowing the reactions. If gravity ever pulled much harder, the core would shrink and heat, speeding them up. The sun behaves like a self-correcting furnace, adjusting without thinking, keeping itself in long, slow equilibrium. For billions of years now, that equilibrium has given it both its light and its shape. None of this means the surface is calm. The visible skin of the sun is mottled with granules, cells of hot plasma rising, cooling, and sinking again, each one the size of a small country. Loops of magnetic field punch through as sunspots, flare, snap, and reconnect, hurling arcs of charged particles into space. Sometimes great clouds of plasma lift off in coronal mass ejections and race outward on the solar wind. Yet for all that movement, the overall outline barely wavers. When spacecraft measured the sun's shape precisely, they found that the difference between its polar and equatorial diameters is only a handful of kilometers compared to an overall size of more than 1 million. It rotates, it seethes, it throws tantrums, but from a distance, it remains one of the roundest things nature has ever made. Part of that comes from numbers being allowed to do their work. Each particle inside the sun is darting around on its own path, colliding, scattering, changing direction constantly. But when you average over countless trillions of those motions, the random bustle smooths into something very regular. A gas whose pressure at each depth is just enough to hold up the layers above it. What feels like chaos up close becomes symmetry when you zoom out. The sun's gravity doesn't end at the edge of the visible ball, either. It stretches outward, shaping the flow of the solar wind into a great bubble, the heliosphere that cradles all the planets. Inside that invisible sphere, charged particles from space are deflected and slowed. In a sense, the sun is not only a round body, it also carries a round domain, a region where its presence quietly sets the rules. One day, that balance will falter. When the sun has used up most of the hydrogen in its core, gravity will begin to tighten its grip there, even as the outer layers swell into a red giant. The star's shape will puff outward and then fall back inward again. Eventually, what's left will be a white dwarf, small, dense, and once more roughly spherical, cooled into a quieter form of the same old truce between pull and push. If the sun shows how gravity can keep even a storm of plasma round, Saturn shows what happens when rotation starts to argue back. Imagine hovering just above its cloud tops. Below you stretches a world made almost entirely of hydrogen and helium, banded in muted golds and creams, spinning so quickly that a day there lasts barely over 10 Earth hours. For something more than 9 times Earth's width, that's astonishingly fast. You're watching a planet trying to be round and a planet trying to pull itself apart at the same time. Where the equator whirls around, everything feels an extra outward push, the centrifugal effect of spin. At the poles, that effect is weakest. Gravity is pulling inward everywhere, but near the equator, it has to fight harder. The result is a compromise shape, flattened at the top and bottom, swollen around the middle. Saturn is still broadly round, but stretched into an oblate spheroid, its equatorial diameter noticeably larger than its polar one. From far away in a small telescope, you can already sense that squashing. Up close, spacecraft have measured it in detail. The poles sit thousands of kilometers closer to the center than the equator does. Saturn wears its rapid rotation like a belt pulled tight around its waist. That speed doesn't just sculpt the planet's outline, it also drives its weather. Winds near Saturn's equator whistle along at many times the speed of the strongest hurricanes on Earth, threading around the globe in pale, hazy bands. High and low pressure systems wrap themselves into storms that last for years. At the North Pole, a standing wave of air currents has arranged itself into a hexagon, a six-sided pattern far larger than our whole planet, maintaining its shape decade after decade as if etched there. Beneath the visible clouds, Saturn's hydrogen thickens with depth, eventually becoming so compressed and hot that it behaves more like a liquid metal. In that deep, unseen region, electrical currents move and twist, generating the planet's magnetic field. That field, unusually, is almost perfectly aligned with Saturn's spin axis, a clue that there is still something about its interior we don't fully understand. Even there, geometry and motion are locked in a quiet puzzle. And then, of course, there are the rings. From a distance, they look like a solid, thin disk. Up close, they dissolve into countless bits of ice and dust, each one following its own orbit, each one feeling the pull of Saturn's gravity and the tug of its moons. Some theories say the rings may be the remnants of a shattered moon that wandered too close and was torn apart. Others suggest they are the leftover material of Saturn's own making, flung outward by tides and slowly ground to powder. However they began, the rings are not permanent. Measurements show that ring particles are constantly drizzling down into Saturn's upper atmosphere, guided by magnetic fields and gravity, a slow, icy rain. Over tens or hundreds of millions of years, much of that shining structure may vanish, swallowed by the planet it frames. Even here, spin and gravity work out a temporary arrangement and then move on. If Saturn spun more slowly, it would be rounder, more like a scaled-up gas version of a quiet planet. If it spun much faster, the flattening would grow more extreme, and the outer layers of gas near the equator could start to drift away, unable to stay bound. Somewhere between those extremes is the speed. Saturn actually has the speed at which gravity still wins overall, but not without being noticeably bent. Taken together, the Sun and Saturn trace out two sides of the same story. In one, gravity and pressure find such a perfect, even balance that a seething star becomes one of the roundest shapes we know. In the other, gravity and spin negotiate a compromise, stretching a giant into a flattened globe and surrounding it with a thin, glittering disk. Both are reminders that shape is just another way of watching forces talk to each other. And yet, as fast as Saturn turns, its spin is still gentle enough that gravity remains in charge. The Sun's storms, for all their violence, never quite break its symmetry. There are places, farther out in the dark, where that is no longer true, where matter collapses so completely and motion becomes so intense that even light has to curve around it. Somewhere beyond Saturn's orbit, In the wider galaxy, there are objects in which spin and gravity push each other to their absolute limits, and the familiar idea of a round surface begins to blur. Before we drift all the way out to those extreme places where even light must bend, it's gentle to pause at something closer, thinner, and strangely undecided. A place where gravity nearly built a world and then, for reasons of motion and timing, let it stay scattered instead. Saturn's rings look, at first glance, like they ought to be the beginning of a planet. So much material, arranged in such a neat, bright band. Surely all that ice and dust is halfway to becoming a moon. But if you look more closely, what you're really seeing is a system that has already found its own kind of balance. The rings are not the start of a world. They are what happens when gravity and spin agree not to finish one. They reach far out from Saturn, a vast, gauzy disk wrapped around the planet like a whisper. And yet, in thickness, they are almost nothing. Tens of meters deep, at most, compared to hundreds of thousands of kilometers across. If Saturn were a smooth ball you could hold in your hands, the rings would be thinner than a sheet of paper clinging around its middle. Inside that paper-thin plane are billions upon billions of pieces of ice and rock, from grains smaller than sand to chunks the size of houses and hills. Each one is in free fall. Each one orbits Saturn with its own precise speed, set by its distance from the planet. The closer pieces rush around in a matter of hours. The farther pieces take longer. This gentle difference in speed, inner parts lapping outer ones, is called shear, and it quietly keeps everything from merging. If two ring particles drift together, they don't settle and stay. They nudge, tap, and trade a bit of momentum. One is kicked slightly inward, the other slightly outward, and their paths diverge again. Over and over, countless small encounters smooth out sharp clumps and stretch them into arcs. For a moment, it looks like a moonlet is starting to form. Then the difference in orbital speeds pulls it back apart. The rings behave less like a pile of rubble and more like a very thin, very graceful fluid, where motion itself is the thing that keeps structure from solidifying. There is another quiet rule at work, too. Saturn's rings lie well inside a boundary called the Roche, limit the distance within which the planet's tidal forces are strong enough to tear apart any object that tries to hold itself together by its own gravity. Beyond that distance, material can gather and stay as a moon. Inside it, gravity stretches and stresses anything large, pulling more strongly on the near side than the far. A small, solid block of ice can survive. A big, loosely held together clump cannot. If something tries to grow large in the rings, Saturn's tides tug at it until it breaks back down again. So the rings sit in a kind of gravitational twilight, close enough that they cannot form a true moon, far enough that they aren't just an atmosphere. They are forever on the verge of becoming a world, and forever kept from it. Even so, the rings are not empty of structure. In certain gaps and edges, a few small bodies have taken shape, tiny moonlets only a few kilometers wide. They orbit inside the rings and along their borders, gently hurting nearby particles with their gravity. As they move, they carve narrow gaps, raise ripples, and create waves that curl around Saturn like patterns in a pond. These shepherd moons don't escape the rules. They simply live right up against them, never growing large enough to be torn apart, never disappearing entirely. They are the smallest possible worlds that the rings will permit. When spacecraft slipped into Saturn's neighborhood and began to watch closely, the picture became even more delicate. Flying through the gap between the planet and the inner edge of the rings, instruments saw fine dust and icy grains moving along invisible lanes. each following its own orbit, each part of the larger pattern. From a distance, we see a smooth band of brightness. From up close, it is almost all emptiness, with just enough matter to catch the light. For a long time, it was tempting to think of Saturn's rings as ancient, as old as the planet itself, perhaps as old as the solar system. Something so grand felt like it should have been there from the beginning. But measurements of how quickly ring material drifts inward tell a different story. Tiny particles are constantly being nudged, charged by sunlight and Saturn's environment, and guided along magnetic field lines down into the planet's upper atmosphere. There they vaporize, leaving faint chemical traces. It is a kind of rain, but made of ice and dust instead of water. When a spacecraft finally dared to plunge between rings and planet, it tasted that rain directly. Tons of icy material falling every second. At that rate, the rings cannot be permanent. They are slowly thinning, particle by particle sliding into Saturn's clouds. Work the numbers backward, and you find something surprising. The rings may not only be doomed, they may also be young. Perhaps they formed only a few tens or hundreds of millions of years ago, a recent flourish in Saturn's much longer life. There are stories that might explain their birth. One of them imagines an icy moon that orbited Saturn in an older, more fragile system. Over time, its path shifted. It wandered too close. Tidal forces pulled at it, cracked it, and finally tore it apart. Its fragments spread into a bright band, flattened into a disk, and settled into the pattern we see now. In that telling, the rings are the lingering outline of a lost world, still circling as a veil of shattered light. In their present form, they are full of patterns written in gravity's handwriting. Wide gaps, like the Cassini division, line up with simple rhythms between ring particles and outer moons. For every orbit a moon completes, a particle in the gap might circle twice or 3 times. That regular tug slowly clears material from those lanes, leaving dark spaces in the brilliance. Finer ringlets and waves mark more subtle resonances, a music of timing and pull that never quite stops playing. The rings also tell a story about what kinds of beauty exist only for a while, compared to the age of Saturn, or the Sun, or the galaxy. Their lifetime is brief, a bright phase between 2 planar states. Before them, Saturn was just a banded giant, round and quiet. After them, it will be that again. For a few 100 million years in between, it wears an icy halo we happen to be here to see. Other planets have rings too, Jupiter, Uranus, Neptune, but theirs are thin and dark, more like soot than fresh snow. Saturn's stand out because they are made mostly of clean water ice, still reflective, still young enough that sunlight scatters from them like light off crushed glass. Even that will change as micrometeorites and radiation slowly darken the particles, grinding and staining them until they shine less and less. Far away from Saturn, new instruments now watch those rings in infrared, measuring how warm they get, how quickly they cool, how the inner and outer bands differ. The inner parts tend to be denser and warmer, the outer more diffuse and cold. Even here, the old rules of balance and efficiency are at work. Energy finds ways to spread. Matter finds ways to arrange itself in patterns that can last a while without tearing apart. When you lay all of this together, the question, why don't Saturn's rings become a planet, becomes something softer. They don't fail to be a world, they succeed at being something else. They live in a narrow band of circumstances, where gravity can gather material, but not quite let it settle, where motion has too much say for solidity to take over. Stability, here, comes not from standing still, but from moving in exactly the right way, over and over again. One day, the balance will shift. The rings will thin and fade as more material rains into Saturn, and more particles are ground to dust, too fine to shine. The planet will return to its simpler outline, almost perfectly round, its adornment gone. Somewhere in that future, nobody will see the wide, bright band we take for granted now. Only the quiet data we've already gathered, and whatever stories we've left behind, will remember that for a brief while, Saturn wore a visible record of orbital motion like jewelry. It's a strangely comforting thought that even in a universe so long-lived, some of the most striking sights are temporary. They appear just long enough for someone to notice, and then they go. Saturn's rings are one of those sights. We happen to be here while they exist, and if something as delicate and grand as that can rise, shine, and vanish on the scale of a few 100 million years, it's hard not to wonder what similar, slower changes might be unfolding on much larger stages. If a planet can gain and lose a halo of light like this, could whole systems of stars, vast disks, and glowing envelopes around galaxies also be thinning, raining themselves inward, and settling into quieter shapes over ages too long for us to see? If Saturn's rings are a story of a world that never quite finished forming, our own sky carries the echo of the opposite story, a ring that did learn to become a world. Long before there was a calm moon hanging over oceans and cities, there was something far more violent. About 4.5 billion years ago, when Earth was still young and half-molten, a protoplanet, roughly the size of Mars, slammed into it. Scientists call that lost body Theia. It struck at tens of kilometers per second, a speed so fierce that rock behaved like water, and both worlds briefly melted into one blazing wound. The impact tore huge plumes of vaporized rock and metal into space. For a little while, Earth was wrapped in a ring not of ice like Saturn's, but of glowing stone. That rocky halo reached tens of thousands of kilometers above the surface, an arc of orange heat circling a world that was hardly a world yet. Gravity, patient as ever, stepped in. Bits of molten debris orbited, collided, and merged. Some fragments lost momentum and fell back to Earth in fiery rains. Some drifted away entirely, but a large share settled into a disk, and within that disk, clumps began to grow. Grain met grain, boulder met boulder, and slowly, the scattered ring thickened into a single dominant body. On human timescales, it would have seemed like forever. On planetary timescales, it was astonishingly fast, perhaps thousands of years, maybe less. As that new body cooled, its surface hardened. Underneath, heat lingered. For a long time, the young moon was not the pale stone we see now, but an ocean of magma hundreds of kilometers deep. Heavy minerals sank inward. Lighter ones floated upward to become the first crust. Only later did impacts carve the basins and dark maria, the features we trace with our eyes from Earth. The clues to this story are locked in moon rocks. Samples brought back by Apollo missions show oxygen and other isotopes that match Earth's mantle almost perfectly. It's as if the moon were carved from the same block, not captured from somewhere else. Whatever Theia was, its material seems to have been thoroughly mixed into ours in that moment of impact, until Earth and Moon became siblings of the same stone. Since then, the Moon has been quietly reshaping Earth in return. Its gravity tugs on our oceans, raising tides that slow Earth's rotation bit by bit. Long ago, our days were only a few hours long. Now they are 24, stretched by that steady lunar drag. At the same time, our planets spin and shape tug on the moon, locking its rotation so that one face always looks back at us. The moon drifts away by a few centimeters each year, but it remains our companion, stabilizing Earth's tilt so our seasons don't lurch wildly from one extreme to another. Calm climates, gentle tides, and the pace of our days are all part of that long, shared conversation. Some scientists go even further and imagine an even stranger early stage. Earth and Theia briefly merged into a single, wildly spinning, donut-shaped cloud of vaporized rock, a synestia from which both the modern Earth and Moon condensed. In that picture, ring and planet weren't separate at all. They were one continuous, glowing structure that later cooled and settled into two bodies. Whatever the fine details turn out to be, the theme is the same. Chaos first, then roundness. A ring of debris, then a world far away. Telescopes now watch other young stars wrapped in dusty disks. In those faint rings of gas and rock, we may be seeing echoes of our own past, 1,000 different versions of the moment when a ring decides, or is allowed, to become a system of planets and moons, and then to circle all the way back to the smallest scale. You can see the same logic at work in something as gentle as a drop of water. Inside the International Space Station, if an astronaut squeezes a little water into the air, it doesn't fall. There is no down to make it flatten and spread. The molecules pull on one another equally from all sides, and without gravity pressing them against anything, the water draws itself into a floating, shining sphere. Touch that droplet, and it wobbles, stretching into an oval, a peanut, a trembling shape full of colors and reflections. Then surface tension, the tiny pull each surface molecule feels toward its neighbors, smooths everything out again. The droplet settles back into roundness, because that is the shape with the smallest possible surface for the amount of water it holds. Less surface means less energy. The same old rule returns. Minimize effort, find balance, become a sphere. If you could somehow enlarge that droplet until it was as big as a planet, the names of the forces would change. Surface tension would give way to gravity. Molecular attraction would be replaced by mass and weight. But the geometry would stay the same. Every point would still be trying to be the same distance from the center. The roundness would still be the sign that all the pulls had agreed. Astronauts play with these droplets, watching dye swirl slowly through them, watching little waves run along their surface. Cameras capture the oscillations, and when scientists compare the patterns to equations written down long ago on Earth, the match is uncanny. The tiny quiver of a water sphere in a spacecraft light becomes a toy model of how stars pulse, how planets deform, how bigger, slower systems respond when you disturb them and let them relax again. In another experiment, droplets are spun gently inside sealed chambers. As they rotate, they bulge a little at the equator and flatten at the poles, mimicking the way Earth, Jupiter, or Saturn puff out at their middles as they turn. A miniature gas giant made of water, drifting in a metal box. Seen this way, it becomes hard to separate the small from the vast. The same shapes, the same tug of war between inward pull and outward push appear everywhere. In ice circling Saturn, in molten rock around a wounded Earth, in gas pressing back against gravity inside the sun, in a droplet the size of a marble floating beside a laughing astronaut. Roundness keeps returning because the universe keeps asking the same question. How can I hold the most within the least? How can I spread energy, share stress, and come to rest, if only for a while? A sphere is the quiet answer that physics gives again and again. whenever it is left alone long enough to think. So when you look up at the moon, calm and steady, it's really the end of a long, wild story. A ring of fire, a sea of magma, billions of years of cooling, pummeled by impacts, slowed and steadied by tides, until it became the soft lantern we know. And when you watch a picture of a water droplet in space, glowing and perfectly round, you're seeing the same story told in miniature. From droplets to worlds, from rings to moons, from storms of plasma to almost perfect spheres, everything we've touched tonight has been a variation on one simple idea: balance. Forces pulling, forces pushing, motion trying to stretch things out, gravity and tension trying to erase edges, and somewhere in the middle, a shape that feels like rest. If that thought brings you even a little ease, if imagining the moon as cooled fire, or Saturn's rings as a temporary necklace, or a floating droplet as a tiny planet makes the night feel softer, I'm quietly glad you wandered here. If you'd like to drift through more of these sleepy journeys with me, a gentle like or a soft tap on subscribe helps others find this little corner called Fall Asleep to Astronomy too. And if it feels right, you can tell me where you're listening from, or which moment in the night keeps you company. Your words, even just a line or two, are like small stars I can steer by when I'm choosing the next voyage. For now, let the shapes we've visited settle in the back of your mind, the roundness of droplets, of planets, of the moon outside your window. Let them blur into a single, quiet feeling of things coming into balance. Wishing you a calm night, a deep, easy sleep, and the kindest dreams in this vast, gentle universe.